Today we will continue to investigate the question, what happens when multiple forces act on an object at the same time? Are you ready? Grab your pencil and your science journal and let's get started. Imagine there is water at the bottom of a deep hole in the ground. You want to get water out of the hole, but you have only a long rope and a bucket. I need your help to develop a solution. What can we do with the rope and the bucket to get the water out of the hole? How can you use what you know about forces? Go ahead and shout out your answer. What if we tied the rope to the handle on the bucket? We can lower the bucket to the bottom of the hole to get water. Gravity pulls down on the bucket and the rope exerts an upward force on it. When we pull up on the rope with a stronger force than the force of gravity, the bucket moves up. Let's draw a force model to show our solution. What forces should we draw? How should we label them? And in which direction should the arrows point? Shout out your answers. Let's include an arrow here to show the force of gravity pulling down on the bucket. We also need to include an arrow here to show the upward force exerted on the rope. Should we include anything else? What about motion of the bucket? Well, since the upward force exerted by the rope on the bucket is stronger than the force of gravity, the bucket will move up. Great. How does our solution compare with an Atwood machine? Shout out your answer. Pulling on a bucket with a rope is like the strings that pull the cups in an Atwood machine. When the blocks move to the right, the string on the left pulls the cup on the left side up. Gravity also pulls down on both the bucket and the cups in an Atwood machine. Awesome. Remember our class claim? Today we will get a chance to apply what we have learned about forces and motions to evaluate our class claim. We will continue to work toward answering the question, what happens when multiple forces act on an object at the same time? Are you ready? Let's get started. Look at this Atwood machine. What do you notice? Hey, do you notice that this Atwood machine doesn't have any cups attached to the block? I wonder what forces are acting on the block when it is not moving. What causes the block to remain at rest? What do you think? Well, the forces acting on the block are opposite in direction but equal in strength. The block is at rest and stays at rest because the downward force of the gravity is equal in strength to the upward force exerted by the table. The forces acting on the table are balanced. Forces are balanced when the forces exerted on opposite sides of an object are equal in strength. Imagine two movers pushing a large box in opposite directions but with equal strength. The box will remain at rest because the forces are balanced. Here's a challenge for you. How can we show a change in the motion of the block on our force model so that the block is no longer at rest? What forces should we add, erase, or keep? I'll give you 10 seconds to think about your answer. Ready? Go. Time's up. So what do you think? I don't think we need to erase anything. Instead, we can keep the upward force exerted by the table and the downward force of gravity. Then we can add a cup with some pennies to the right of the block. Let's add 4 pennies. When we add this new force, the block will move to the right. To show this motion, we can add a motion arrow and a force arrow to the right. The block's motion changes because the forces exerted on opposite sides of the block are unbalanced. Forces are unbalanced when the forces exerted on opposite sides of an object are not equal in strength. This time, imagine one mover pushing a large box with more force than another mover. Because the forces on opposite sides are not equal in strength, the forces are unbalanced. The box moves in the direction of the stronger force. Here's another challenge for you. Remember when we saw this video clip of an Atwood machine? It has 2 cups, one on each side. Each cup has 4 pennies in it. Do you remember what happens when I let go of the block? Let's watch the video clip again. Yes, the block does not move. Are the forces acting on the block balanced or unbalanced? How do you know? I'll give you 10 seconds to think about this challenge too. Ready? Go. Time's up. In this scenario, the force of gravity is equal in strength to the upward force exerted by the table. The strings also pull the block in opposite directions but with equal strength. The forces exerted on the block are balanced, so the block's motion does not change. Wow, was balanced your answer? We just learned a lot of new information about multiple forces acting on an object. Now is a good time to revisit our class claim. Let's reread the first part. When the force exerted on any one side of an object, left, right, up, or down, is stronger than the force exerted on the opposite side, the object's motion changes. Do you think we have enough information to update this part of the claim? I think so too. How can we make our claim more precise? Well, now we know that when any of the forces exerted on an object are unbalanced, the object's motion changes. Great. Let's now reread the second part of the claim. When the forces exerted on opposite sides of an object are equal in strength, the object's motion does not change. Do you think we have enough information to update this part of the claim? I think so too. How can we make our claim more precise? Now we know that when all of the forces exerted on an object are balanced, the object's motion does not change. Your task for today will be to update the class claim and provide evidence and reasoning to support this claim in your science journal. I'm so excited about the information we've learned so far about balanced and unbalanced forces. Where have you seen examples of these types of forces in your life? Your final task for today will be to summarize your knowledge of forces. I can't wait to learn more in our next lesson, can you? Hi, students, and welcome to today's lesson. I'm Ms. Lee. Today, we will continue to investigate the question, what happens when multiple forces act on an object at the same time? Are you ready? Grab your pencil and your science journal, and let's get started. Remember this photograph of dolls playing tug-of-war with a toy? Have you ever played tug-of-war? When the whistle blows, both teams exert a force on the rope by pulling in opposite directions. If the forces are unbalanced, then the flag will move in the direction of the stronger team, and that team will win. But what happens if both teams pull the same strength? If the teams pull the same strength, the flag in the middle of the rope remains at rest. The forces are balanced, so no one wins and the game is a tie. One of your tasks after our last lesson was to provide evidence and reasoning to support our class claim. When any of the forces exerted on an object are unbalanced, the object's motion changes. When all of the forces exerted on an object are balanced, the object's motion does not change. What evidence did you find to support this claim? Let's find some evidence together as we examine one example of a balanced force and one example of an unbalanced force. Let's revisit our force model of the Atwood machine to help us. This model has 25 pennies on the left side and 10 pennies on the right side. How does the block move in this model? Point to where the block moves. Yes, the block in an Atwood machine moves to the left when more pennies are placed in the left cup than in the right cup. How does this evidence support the claim? Well, when more pennies are placed in the left cup than in the right cup, there is a stronger force exerted on the left side. The forces are unbalanced, so the block moves in the direction of the stronger force. Let's observe another Atwood machine force model to see if we can find even more evidence. How does the block move in this model? Shout out your answer. Yes, the block in an Atwood machine does not move when there is no cup attached to either side. How does this evidence support the claim? Well, when the block is at rest without any cups attached, the downward force of gravity and the upward force exerted by the table are equal in strength. The forces are balanced, so the block does not move. Hey, I think we now have enough information to update our anchor chart. In our forces section, let's add, gravity is the force that pulls objects toward Earth. Also, forces that are unbalanced cause an object's motion to change. Forces that are balanced do not cause an object's motion to change. Your first task today will be to update the anchor chart. Let's also revisit our anchor model. We've been talking about the motion of a soccer ball on board the International Space Station and on Earth. How can we use what we've learned about forces acting on an object to update our anchor model? Let's compare the forces acting on the Atwood machine to the forces acting on the soccer ball on Earth. What forces should we add to our soccer ball model? On Earth, we need to show gravity pulling down on the ball and the ground pushing up on it, just like the block on the table. Also, I'll draw an arrow to show that a foot exerts a force on the ball during a kick. Let's now update the explanation. We can add, before a kick, the soccer ball is at rest on the grass. Because the force of gravity pulling down on the ball and the force from the ground pushing up on the ball are equal in strength. Now that we know more about what happens during a kick, let's add that during a kick, a person's foot exerts a force on the ball, which causes it to start moving. We also now know about gravity, so we can add a sentence that says, since the ball stays on the ground the entire time, the force of gravity and the force from the ground stay balanced. Great! Now let's use what we know to update the International Space Station side of our model. What information should we add? During a kick in space, a foot also exerts a force on the ball. Now let's update the explanation. Now we know that during a kick, an astronaut's foot exerts a force on the ball and it changes speed and direction. We also know more about what happens after a kick in space, so we can add to the next sentence as well. After a kick, it continues to move through the air until it hits something. For example, a wall or another astronaut, and another force is exerted on it. Your second task will be to update the anchor model and explanation in your science journal. Guess what? Let's watch a new video clip of astronauts playing soccer on the International Space Station. As you watch, focus on the motion of the soccer ball and the forces exerted on the soccer ball. What do you notice about the motion of the soccer ball on board the International Space Station after it begins to move? The ball seems to move in a straight line with the same speed until an astronaut kicks the ball and changes its direction. Do you notice anything else? Oh, yeah. Once the ball is moving, it bounces off walls and people until something makes the ball stop, such as when an astronaut grabs it. What do you think would happen to the soccer ball's motion if it did not come in contact with another object or person? I think the ball would keep moving unless something caused its motion to change. Why do you think a soccer ball on Earth doesn't keep moving forever after it is kicked? The ball always eventually slows down and stops. Do you think a force must make the ball slow down and stop? I think so. I wonder, what forces are exerted on a soccer ball on Earth after it is kicked? And can these forces explain why the soccer ball slows down? What do you think? I don't think we have enough information to answer these questions, do you? We'll need to investigate further. In our next lesson, we will investigate a force that can cause objects to slow down and stop. I can't wait to see what happens. Let's review your tasks for today. First, fill in the blanks to update the anchor chart. Second, update the anchor model and explanation.